At Qualcomm Technologies, we are not only leading the 5G millimeter wave technology evolution, but we are also committed to make millimeter wave a commercial success. There are many ways that an operator can go about deploying millimeter wave in their 5G networks, but one common challenge they face is how to arrive at the most efficient network topology. Today, I will share with you our R&D effort in adopting machine learning and optimization techniques to explore the use of different millimeter wave infrastructure options. Our approach to a more intelligent way to millimeter wave network planning involves three steps. The first is creating a digital twin of our targeted deployment based on readily available databases such as Google Street View. Then, we simplify our digital model and balance design trade-offs using machine learning-based object recognition, clustering, and pruning. Last, we evaluate the different millimeter wave infrastructure options that can be used to arrive at the most optimal design utilizing all the network node types available to an operator. Here is a simple graphical representation of the different millimeter wave topology options. We have diverse connectivity options and node types such as small cells, integrated access and backhaul, simple and smart repeaters, and more. Each of these options has pros and cons, and they can be deployed to meet different network design objectives. As an example, we're looking at a small cluster in Tokyo. Our machine learning algorithm takes open source or other available data as an input and efficiently identifies the different physical elements that can impact a millimeter wave deployment, such as poles, buildings, foliage, and other street furniture that's relevant. We can perform comprehensive network analysis to show the cost and performance of different deployment options. We use another city, Philadelphia, to illustrate this. Here we see an example using small cells only, where a fiber drop is connected to each new small cell location. A second deployment option utilizes smart repeaters and integrated access and backhaul in addition to small cells, which can simplify deployment, deliver enhanced performance, and additional cost savings. What we learned is that there is a lot of design versatility when it comes to deploying millimeter wave, and our approach allows us to quickly weigh the different options. And of course, we can readily expand this analysis to a much bigger area. In conclusion, we are taking a comprehensive approach to designing and optimizing 5G millimeter wave networks. Our approach that combines machine learning and optimization techniques could greatly simplify the network planning process. There is a lot of different tools or node options in the deployment toolbox, and our models can be configured to evaluate different options to meet the system requirements. And lastly, there is an expanded applicability of this technique to other deployment scenarios and uses beyond millimeter wave network planning, such as for sub-7 GHz and indoor deployments.
So while 5G mmWave continue to evolve, bring better performance and efficiency, it is also expanding its reach to new device type and tiers. In Release 17, the Reduced Capability or NR-Light work item defines a new mmWave device class that can be more efficiently support the growth of IoT device while delivering the wideband and low latency benefits of mmWave. This is a system simulation of a 5G mmWave network operating in the 26 GHz band with 400 MHz bandwidth. We took Frankfurt, Germany as the basis of our simulations, where there are 92 mmWave sites in total, covering an area of approximately 1 square kilometer. In the baseline scenario, we only have a Release 15 mmWave eMBB device enabling the system, operating in the entire 400 MHz allocated bandwidth. As you can see, there are currently 228 devices, taking up approximately 48% of the total network resource. In the second scenario, a low number of surveillance cameras were added to the overall simulation. These are reduced bandwidth NR-Light device, utilize 100 MHz of spectrum for uplink communication. This new mix of 456 devices added 10% to the overall capacity, now to a total of 58% network resource. Now we add even more NR-Light device to the system. We see the number of total NR-Light device now going up to significantly to the 912, while only increasing overall network resource utilization to about 68%. Looking at these three scenarios, we can conclude that a mmWave network can efficiently support a large amount of NR-Light IoT device, coexisting with eMBB device, and without significantly impacting network resource. In this demonstration, we will see how 5G mmWave can support diverse connectivity needs in new verticals. As example, we have simulated a 5G mmWave private network supporting smart factory use case. Here's a smart factory floor map is about 34,000 square feet with a 12-feet ceiling height. We have 16 mmWave sites covering the space, including the factory floor and some office space. The mmWave network operates in 28 GHz band with 800 MHz bandwidth. The first type of 5G device in the factory is enhanced mobile broadband, including both smartphones and always connected laptops. In this setup, this device have an average downlink throughput of over 1100 Mbps. Boundless extended reality can enable many emerging Industry 4.0 use cases, such as guided maintenance and task execution. To support immersive, augmented reality experience, heavy processing is done on the edge server, while lighter load compute can be processed on device. With this, boundless XR as a traffic requirement of 100 Mbps with a 10 millisecond latency bound in the air interface. As we can see here, this requirement can be met. 5G can also cut the wire for extremely high-performance industry automation use case. Time-sensitive networking, coordinated multi-point, and EURC are key 5G capabilities that can deliver 6 nines of reliability with millisecond level latency. As shown here, the mmWave system can meet these requirements. In addition to supporting high-performance applications, mmWave can also scale down to support lower complexity IoT devices, like industry camera sensors, using just a 100 MHz bandwidth. We can see the system supporting a large number of devices with a small impact to network resource utilization. In conclusion, a 5G mmWave network can provide seamless connectivity to a wide range of use cases, allowing enhanced mobile broadband, high-performance industry automation, and low complexity IoT use cases to coexist.